If we know about the standard model, why we believe in the Higgs mechanism, why we believe that the physics of the standard model is deeply connected. If I ask you, can you give me some reasons why you would believe that, or what I said, that the Higgs mechanism is the source of neutrino mass? After all, remember, I started constructing the standard model without any Higgs. I used the Glashow's 1961 model, wrote down the gauge theory and said, oh, I can just give particle masses. Can you think of some well, remember the first thing we derived was this nice relation mz cosine theta w equal mw. This came directly from the Higgs mechanism, okay, and it works with a great precision, okay. When something works with a great precision, you tend to believe it seriously. What else? Well, we found the Higgs, and you've seen, we found it, the decays that have been probed, remember? I'll come back to them, I'll have to say a few more words. It was gamma gamma, WW, ZZ, and now the beginnings of BB bar and tau tau bar. So slowly the evidence is being accumulated that actually the fermion masses, and not just the gauge boson mass, but mass in general, seems to have origin in the Higgs mechanism. We are yet far from a rigorous complete proof. We want to see all the channels, okay. That's great. What we like even more is the fact that we started saying that the standard model failed when it came to neutrino, and that is due to its inherent asymmetric lecture. Let's forget it works for the time being. Okay? These are my protagonists now. And let me go directly into the unitary field, where there is just the physical Higgs scale boson. Okay, reset. Electron got the mass from the Yukawa coupling. Neutrino. Well, first, let's maybe try to keep it if I don't have to erase it here. We've learned that besides the usual Dirac mass term, you actually did it in your first exercise. Summarize once again that I can write the following Lagrangian for the left-handed field. Y, two-component spinor, y factor of 2, you remember? Why do I write it m over 2?
2 left and right.
There are actually two terms here, and this is best seen when we introduce a 4-component spin. The reason I wanted to leave it there, which I called psi L plus C psi L bar transpose. This guy is actually right-handed. When you do your charge conjugation, the left goes to right. This, we remember, we saw it to be UL I sigma 2 UL star in terms of the we found out that this Lagrangian becomes 1/2 sine bar gamma mu d mu psi m minus mn psi m bar psi m. I will probably stop doing that when I speak on my Raman mass and keeping explicitly the Majorana index. It will have to be understood from the context, okay? And it simply means that this is actually a 2-component spinor written in a 4-component form. The reason I do it because we have Feynman rules in the 4-component form. But the physics is hidden here. And the point is that C psi L bar transpose, you can actually write it like this if you wish. I could write to emphasize. See, it has to do with, when you write it a field like psi CR, you have to be very careful what comes first. Okay, I put a bracket here explicitly. Why? How do I know that? Well, because when I compute it, I get I sigma 2 UL star. Well, this is a right-handed field. In our convention, right-handed fields are the one at the bottom and the left-handed fields, due to our definition of gamma 5. Where is the physics hidden? In both ways. It's hidden here. You and I have been used to the claim, as Feynman taught us, okay, that's a conservation charge in QED. When you write the Feynman rules, the fermion line has to propagate. You can never break the fermion line. But we just did. This is what Dirac missed, what in his great work, Majorana, saw. That here I'm explicitly breaking a fermionic line. Very often when we speak of Dirac mass term, which was psi bar psi, which required explicitly two different spinors. Obviously, this I should represent like this. A left-handed field enters and the right-handed field leaves. And very often you will see we call it mass dispersion to emphasize if something goes through the mass term, we want to say that we have to keep the continuity of the mass term. Okay, this is just to say, in my Feynman diagram, I should check it. Actually, the result will go through the mass term. Let's call it my Dirac. Manifestly, you see, psi r comes out, psi l enters, right? We have a situation that so it's good that I'm late. Sometimes, right? But my random mass term does something opposite. Actually goes like this. Psi L enters and psi L enters. So when we want to emphasize this, what is this? It's a violation of that particular quantum number. If the guy carries charge, it will be violation of charge. If the guy carries baryon number, it will be violation of baryon number. Whatever the quantum number the charge, the field carries, the charge will be broken and it's manifest here. It's sort of annihilating, right? It looks like really there are two of the states we are annihilating into nothing, okay? And we said the only true neutral particle that we know of, or what could be a neutral particle, everything indicates neutrino, is then ideal candidate. If there are such particles, this is the candidate. And there is you see, in his genius, Majorana imagined this as a possibility. But we are sort of, if you look at the people in our field, in the neutrino field, most of us believe in this for the following reason. Neutrino and electron, except for the charge, are basically one and the same particle. Look at the weak interactions, right? They live together. Look at them here. W doesn't even know that there is neutrino and electron. This is one guy. And yet, we know that neutrino mass is less than 6 order of magnitude smaller than electron mass, which is very puzzling. But the only distinction is the fact that neutrino is neutral, so that could be explained to me. So my Rana picture could be nice. I'll motivate it in 3 different ways. And then of course I allow for the visibility. Who asked me the other day if neutrino could still be Dirac, of course. Experimental design. I think you mentioned that. Okay. So you can see here the violation of the left-hand bar. I cannot overstress this, and you will hear me repeat it many times. Or you can say here, you say, no, but I don't see it here. Look, it's psi bar psi. Well, it's here. This crazy guy that I call Majorana is half particle, half antiparticle. Okay. Once again, I'm breaking a quantum number by 2 units. I'm putting together particle and antiparticle, that's breaking down by 2 units. So let's speak of a lepton number from now on. we have delta L equal 2 possibility. You agree?
Couldn't we say that the lepton number of neutrino is 0 because it's half particle and half antiparticle?
No, we can't say that. It's defined here. I start. How do I define the quantum numbers? I define it here. I first define the particle numbers by what is essential in my interaction. Okay, and that's the interaction with the W boson or the present here. This I say. Then I define the lepton number. And then I look whether it's broken the same way that I would define the charge. If the particle is interacting with the photon, it carries charge. And then I may see whether there is some small breaking in the mass term or in some other additional thing, okay? And we gave it a lepton number because remember, that we found processes, okay, and this is from Mehmet, who managed to get into SISA, but admitted to me the problem of producing some of the weak interaction. This is good, you see. It's good and bad. I would like you to get out of the course knowing and remember things, but it's not so important as long as you can then reproduce them, okay? It's physics, it's not about knowing. It's about being able to do things with your knowledge. And so typical process that we have, there is always this associated lepton number. Okay, we decided to call this antineutrino because always go with the electron, therefore we could say that the lepton number is conserved. For example, when muon decays into, no mu comes out. Any which process you look at, you can give me some other, you can look at the scattering, there is always associated neutrino to an electron. So you can imagine, then when you see something, decade after decade, then possibility that you see a violation of that becomes extremely important.
In my case, we will have vertex where the two particles comes out from it?
And that's precisely what we want to see now. Very good, this is what I want to come now. So I need to imagine the process, you actually knew it, but I want to come as if you didn't know it with your help. I need to think of the process. If this is true, that somehow I should get a violation of lepton number. Something should happen that is not like this. This is not a good way to look at it. Because I get this neutrino and a neutrino, so therefore I need a thing in which I could go through this. I need this to be an internal state. This would be ideal. Okay, so if I want to go through neutrino, then neutrino would be virtual particle. And therefore I would have to have two electrons coming out. And that means, this is in 1935, Maria Geppert-Mayer came with an idea and says, sometimes you don't get the beta decay. Why? Because the outer nucleus is heavier. So you may happen, I think the nice example is germanium, who should decay into arsenic in plus electron plus antineutrino. However, if this guy is heavier, and it turns out, then this cannot happen. What can happen? It can get into selenium. But the difference, the baryon number is 2, so I would have a double beta decay. 1935. Geppert-Mayer. Imagine this process has been observed. It's very rare, obviously. You need a simultaneous decay of I don't remember the quantum numbers. We could reproduce them. They were. I should have 2 protons more, right? What is actually happening? 2 neutrons are decaying into 2 protons. Okay, for us it's important. Okay. Here the daughter nucleus selenium is lighter than germanium. The total number is 76, I believe. And then I think it has 34 protons that become 36 protons. Something like this. doesn't matter. You won't remember it so much, right? I can see the logical part, okay? I'm trying to motivate it. You can see I'm not really a true phenomenologist as much as I try to motivate. Here, what I'm doing here, as you can see, I'm on a mission is somehow to make you appreciate the beauty of particle physics, which uses the tools of particle physics, which is field theory, in order to come up with fundamental theories of nature. No matter how much you may like strings, please learn field theory very well, because field theory is definitely a tool of particle physics, and strings cannot be. Maybe in the future it will become, but obviously, at today's physics it is field theory. So what is happening here? Neutron becomes a proton, according to Barry and Meyer. Now we know in a modern language by meeting a W. W is emitted from here, W minus. What is really decaying is a down quark in the neutron. This much you know. The electron comes out, so that means the neutrino is entering here in the usual manner, and neutrino is entering here. Yes. So I'm getting two neutrinos entering. It's equivalent to two antineutrinos going out. Please keep that in mind, always. This is a double beta decay. These two are final states. These are the longest measured lifetimes in H. You have some idea how long this takes? I mean, neutron decay, after all, is a more or less. Some of you knew the time more or less. Someone knew, I remember roughly.
It was me.
Huh?
It was me.
Muon decay. Tell me some decay you know. Something you know about weak interactions. Let's see.
10 to the minus 6.
10 to the minus 6 seconds. Wait, that's a natural time for weak interactions, okay? And you would notice if you put other numbers. But neutron decay is much slower, and remember the reason?
It is decoupled because it's okay.
Normally when I decay, what is the decay rate decided by? If I write a decay rate, it's going to be given by the strength of the interaction, that's for sure. The stronger the interaction, the faster I will decay. So for example, weak interactions with words like G Fermi, you know that. Typically you would expect that the weak decay, let's give it a little thought, a little digression, 2 minutes, would be G Fermi square, you agree? If the strength of the interaction is G Fermi, then it should be G7 squared. But the decay rate is on the dimension of energy or mass. Therefore, what I need here is fifth power. So typically, it's the particle of the heavy particle that is decaying into lighter particle. Okay. So the particle P is decaying, and I expect the decay rate like this. And when I do it for the muon, next example here, I take particle to be a muon, I will get gamma is 10 to the minus 6 seconds to the minus 1. I don't remember. But I know that lifetime ends up being 10 to the minus seconds. You help me anyway. This is true, what you knew. Neutron, however, so it's like equivalent saying that tau neutron, tau muon is 10 to the minus 6 seconds. Often you will hear particle physics saying that it's about 10 to the 4 centimeters. Because C is one we speak of decay rates as centimeters. Sometimes when we want to see how long will muon travel. Okay. Now, if I take this particle, sorry, this is not proton, this is P, it's for particle, okay, which is decaying. If I take P to be neutron, I would expect the lifetime to be shorter because, look, the rate is, I have a stronger rate. Yet it takes, well, you don't know, it takes about 10 minutes. What?
Smaller phase space.
Yes, because it's not mass here. I've cheated here. It should have been particle initial minus particle final, if something like this, right? Something like this maybe to the, well, I don't know how it will go, but more or less may go with squares, whatever. What matters really is the mass difference, and proton and neutron are basically having the same mass. On the order of GeV, the mass difference is tiny, about MeV. So it takes much more time for neutrons. So lifetime of a neutron is about 10 minutes. And yet this double beta decay, which we could call this tau neutrino beta decay, tau 2 neutrinos, double beta decay, or 2 neutrons, often it's called or tau, let me see, tau beta with neutrino, nu, something like this, I don't know. We just say tau neutron. Tau 2 neutrino, or tau two beta, 2 neutrinos, is, someone knows any idea? Can you, it will be hard to guess. It gets to be very tiny. You have no idea. Sorry that I want us, if I stop here and if I just don't write the numbers, maybe they will stay, okay? A feeling for the numbers occasionally may be useful when you have to think about future physics. It's about 10 to the 21 years. It's a small probability to have two neutrons decaying simultaneously in the nucleus, okay? So it takes much more time. Now there was Mahmoud's question, can I imagine this really taking place physically? And this was the idea that came to Racah vaguely and Fourier's theorem in QED after he saw this great work on Majorana. 1937, 2 years later, Majorana writes this paper. Actually, how Majorana writes this paper, it's one of these mind-boggling stories. Yes, please.
When you saying simultaneously, you mean like for the two decays to happen at the same time?
I need two beta decays to happen simultaneously. In the same, I'm thinking of a nucleus and I have two of these neutrons to decay. It takes time.
But is it small because you say simultaneously, so that you need to take difference in time, let's say very small, so like by uncertainty it will.
Well, I mean, it's not fair for me to tell you, we would have to write down to estimate this, okay? And I don't feel like doing that, but you see.
I mean, do this happen like in the normal way, but it's
yes,
with a little bit, with the sometimes different in just like very quick, so not that that.
Well, it is the usual beta decay only happens to have twice. It should happen. The double beta decay should happen simultaneously, and then the probability is smaller. Then there should be intuitive feeling now why it comes to 10 to the 21 year. I won't do that. I wouldn't be doing a fair job if you wish, we can try to put a number later on when it won't be very illuminative. We'll have to understand some of the nuclear physics aspects of what is going on here.
But I mean, what confuses me when you say simultaneously also? Because let's say both reactions will have a...
No, it's not one neutron decaying here, one decaying here. They have inside the same nucleon. I have to have the probability. All these are probabilities. Decays happen with some probabilities, right? Remember, the more particles you have, you get. It's a statistical thing. Decays. It's not something in this micro world of ours. Well, I'll be talking about this in a little later. Okay, let's see if you wanna come back to this question half an hour from now. Oh, I should have said here, if I have this, I have also the Hermitian conjugate. You agree? And that's opposite. If here two neutrinos are entering, what is happening here? 2 neutrinos going out. So I should have reminded you that there was also this, and that will be psi L going out, psi L going out. They always go together. I will do this as if you have not discussed this with Alexei. It's very important. Okay, these things may have been vague, or you may have half forgotten them. Here is one of the holy grails of modern particle physics. In a sense, this is where the most of the experimental activity now has turned into it. So we have to do it with you. I would say, in the terms of neutrino physics, this to me is equivalent almost to finding the Higgs. To me personally, I'll try to convince you of that. So, in other words, if I can imagine this process, and if neutrino is the Majorana particle, I expect this to happen. This is like a sense. You can think of this guy annihilating or creating something. You know, and this process has been called 0 neutrinos, 2 beta. Neutrino less, double beta decay. Terrible name. Crippling, sounds like an evil. It's a beautiful process. Somehow there is a magic here. I'm creating electrons out of nothing. Right? They are just nuclei, and I'm creating electrons, really. I'm violating lepton number. I'm doing this incredible thing. Okay, now this is, we are desperately seeking for this. The reason is because we've never seen it. It was imagined in 1938, elaborated in 1938. 80 years later.
How does the experiment work? That they put large amounts of these nucleus and see?
This is an interesting question, how you would... yes, of course, everything is statistical. How would you see it? Everything is, of course, statistical. I'm glad the same way you would look for the proton. Remember what we said the other day? We were saying if the proton decays, let me take a lot of them. But what I will have to see, and we may come to that when I speak of proton decay, and it's good to remind ourselves here. I'll erase this. This is less important. So my run of work was 1937. A year later, Majorana was to disappear forever. It was never found. And there were legends about him for the Procura, as you say in Italian, police headquarters of Palermo and Rome. The case is closed. Finally, only a few years now, they think that he actually survived his disappearance and lived in Venezuela for many years. It's far from being convincing. There were possibilities of suicide that people talked about. He disappeared while on a boat trip from Palermo to Napoli. He was Sicilian who got a job in Napoli. And the reason he got a job, he told his friend, Enrico Fermi, that he would like to come back and do physics, okay? He disappeared from physics for a few years, okay? And since Fermi knew that he was a genius, Fermi arranged, he wouldn't publish, he basically had almost no publications. He arranged a position which is called direct fame, under the condition that he writes a paper. So he took it out of the drawer, the thing which was shaped, the particle physics of neutrinos, forever. He had it there, but he wouldn't publish it, okay? This is the, this was Ettore Majorana. I wish I could say the rest is history, but we haven't seen this yet, so I can make some other little stories about Majorana, very interesting, okay, but thank God that he published this. It would be very hard to get a job today like that. Publisher parish has become much more, you know, the field is bigger. Obviously, the measure of this is the mass of neutrino Majorana mass. Therefore, I can phrase the lifetime in terms of the mass. It's not easy to get that connection. So, a few important facts, and then we try to derive that. first, how would I see it? How did we see neutrinos? Why were neutrinos suggested?
Because of the continuous spectrum of the electron.
Because of the continuous spectrum of the. And sort of ironically, we should see the opposite. If neutrino is a Majorana particle, you will just simply compute the energies of two electrons, and there should be no energy of two electrons must be fixed. It's going to be a line with some uncertain. There will not be a continuous distribution that you got in the case of so it will be sort of the anti-discovery of neutrino, because now we have to anti-discover neutrinos. We have to see that it's possible to get the electrons. Up to now, electrons can never appear. Ever. You have a process that has to do with nuclear physics. You always get his sister or brother or whatever, this guy neutrino together. This is how we would see it, and of course statistically I need to have a lot of them in order to come up with the lifetime. 0 nu 2 beta actually is getting now close to 10 to the 25 years. The experiments it used to be quoted as 10 to the 24, but the number is, I think it's closer to 10 to the 25 years. It has not been observed yet. Some years ago in the 90s, the greatest experiment, the biggest experiment was Moscow-Heidelberg experiment. And a funny thing happened. When the experiment was over, the head of the collaboration, Klapdor, Klein-Grotehaus, known as Klapdor, announced that they've seen. It was very interesting, this. He and maybe one or two collaborators later joined him. The rest of the team claimed they didn't see neutrinos double beta decays. That has turned a lot of attention. Okay, now we know he was wrong, because there are better experiments today, and they've come up with the. I'll send you a list of these, just that you appreciate that. This is now has to be interpreted what it means for the neutrino Majorana mass, and it's surely less than electron volt. You will see even people writing maybe 0.2, 0.3 electron volts. I'm not an expert to be able to judge the quality of nuclear physics. You see, in order for me, from this result, to give you the limit on neutrino mass, I have to be in control of uncertainty of nuclear physics. So let's quote it conservatively. This everybody agrees on, for sure. Which is okay, not a big deal. Neutrinos are lighter than that. We know that. But, okay, they could still be degenerate. Well, I'll come and remind you of neutrino mass, what we know from neutrino oscillations. Okay, at this point, let me not say too much. I shouldn't have said what I said. Now you see, the way I drew it is not the way you would have. When we work without four-dimensional fiber rules, we like to follow the fermionic line. This is the first homework. This is why I introduced the Majorana state, so that we have the usual 4 fermion rules. But I can say it in a different manner. Which maybe is, if there is a mass term like this, we could arrive at Majorana. One way was very intelligent here, thinking that we can anti-symmetrize two spinors. Okay, this is the analogy with quantum mechanics. When I take two spinors and I anti-symmetrize them to get a singlet. After all, this is just an anti-symmetric tensor between the two spinors. Or another way to arrive at Majorana could be said, if psi bar psi is invariant, then psi c bar psi is also invariant. That was part of the first homework. If psi is a spinor, so is psi c bar. So is psi c. This is equally spinor as psi. So this obviously must be invariant. What would this be? But this is psi c is c, psi bar transpose bar psi. So what is this? This is C gamma 0 psi star, dagger gamma 0 psi. Psi C bar. And this is psi transpose gamma 0 C dagger gamma 0 psi. This is M Majorana. Remember that gamma 0 will change, will anti-commute because C has gamma 2 inside. So I will get psi transpose minus C dagger psi gamma 0 square is 1, and this is M psi transpose C psi. Psi dagger is psi transpose is minus C. These are the properties of charge conjugation. This is a generic property which can go beyond our basis. Okay, and normally this is the term I wrote. Let's put it a chirality. If you wish, you will get to the same term. Called psi psi left-handed. Okay, I wrote in the 4-component NOR, but we can do it for the 2-component spinner. So this is sort of a way to remember. This is a kind of 4-component, a direct way of writing a Majorana term. Either think of 2 neutrinos entering or 2 leaving, or think of the neutrino entering, anti-neutrino leaving, which is equivalent. Why am I saying this? Because I would actually, I'll come to this. Let's first establish this. Let's see it explicitly. The way I would write it, I can write it like this, but this would be equivalent of EC entering. If I say that electron going out is equivalent to EC entering, I can follow the electron line, and I can use the usual 4-component rules. The only thing, I'm used to writing weak interaction in terms of the electron, not in terms of EC. So here is one useful up to a sign. Let's derive it. This is equal to nu CR bar gamma mu ECR. If I'm right, what I keep saying, if I'm right, let's see it explicitly what it means when I use these words. I'm saying it's the same thing when the electron is leaving or anti-electron is entering. So if I'm right, this should be true. The electron going out should be equivalent to positron entering. But remember, when you go from electron to positron, chirality changes, just like the parity. So it should look like this if I'm right. So let me compute this. Nu CR bar gamma mu ECR. What is this? This is C mu L bar transpose bar gamma mu C E L bar transpose. Remember my convention. There is a, if you wish, how to decide. I first have to see something, okay, play a word in English, in order to decide what chirality it has. So I mean this. For example, there is a beautiful paper by Weinberg that I'll be talking about, okay, which he does the opposite, okay. It drives me crazy. I had always problems with notation. I don't know if you look at Weinberg's field theory, it's a fantastic, incredible encyclopedic book. I suffer with notation, especially in the supersymmetric part. So whenever you read something, you have to see whether you first see it or you first are, you understand, is this ECR or ERC? When you go from particle to antiparticle, please remember the chiralities change, just like in case of parity. Please remember that. So this is what I mean. And this is manifest with this. We saw that when I act on the left-handed guy, I get it in the lower component. Okay, we've checked that. So let's go on. What is this? Please must make sure that I don't make even a tiniest mistake, because I have C gamma 0 nu L star dagger gamma 0 gamma mu C E L bar transpose. Correct? This is C nu L bar transpose. So what is this? This is nu L transpose gamma 0 C dagger gamma 0 gamma mu E L bar transpose. I think this is correct what I wrote, but maybe we pause. I'm always thinking gamma 0 to be real, so I don't write gamma 0 star, okay. I'll do the calculations in my basis, okay, that you and I have accepted. Okay?
There's a C or?
Oh, did I lose one C? Yes. Thank you. So what happens here? Gamma 0 goes through C but changes the sign. So this is minus nu L transpose C dagger gamma mu C E L bar transpose. Here is the definition of charge conjugation. Usually it's written as C transpose gamma mu C is minus gamma mu transpose. This is the definition of charge conjugation. You defined it this way when you wanted to show that psi C is a spin. And C dagger is equal to C transpose. And it's minus C. So this is nu L transpose, gamma mu transpose, E L bar transpose. Now I am going to change the order, so this will be E L bar, but there is a minus sign, gamma mu nu L. So there is a sign. And please, this is what I will mean always. This is what Feynman meant. This is what you are always told. A particle entering is an antiparticle leaving. You can see it manifestly here, okay? Just keep in mind that chiralities will change. I can speak, and you should learn this, either a left-handed electron and a right-handed electron, which I did in the standard model. I could have done, as many people do, instead of working with VR, I could have worked with ER star. After all, whether I work with a field or entire field. Well, this is not really a spinner. Yes, it needs sigma 2 and so on. So what we say that instead of this we work with EC left-handed. This is equivalent. EC left-handed is CER bar transpose, which is ER star. You can work with ER or ER star. The advantage of here, you're working both times with the electrons, so it's kind of nice to have electron. What is the advantage here? That you're working with the fields of same chirality. So for example, if you like to unify them, like the practitioners of grand unification, then you have to put together the fields of the same. You cannot put two different chiralities in the same multiplex. You will break Lorentz symmetry.
Can we work with, instead of right-handed electron,
right, with a precisely. We could work with a left-handed positron. And I'll show you how you work with that. We'll have to learn that. Now that we are going into the processes like this, and that's what I'm doing, by the way. I'm saying you can either work here with a left-handed neutrino, or you can work with a right-handed antineutrino. I've done it implicitly when I wrote this.
But I was thinking numbers are different for both chiralities, doesn't it?
What do you mean by both correct? This is the anti-state of this. Of course it has to be. I can either work with a particle or it's anti-particle, it's up to me. When I say that I work with the Higgs doublet phi, you can work with phi tilde or phi star. That's equally good field. After all, what comes first? No, they are equivalent. You work either with this or with this. They are made out of the same state. This is ER and this is ER star. I like to work with ER, but you say no, why should I? I like to work with ER star. It's important that this has nothing to do with this field. You can see that they have nothing to do with each other. They're different entities. It's not that this is R on the same field. This is when I put them together in a four-component strange manner. This is one field, this is another field. If you think you've gone through this, I'm going to have to erase this. I don't want to erase these fundamental issues, okay? These few next lectures are touching into the basics of particle physics, field theory, Lorentz symmetry, and so on. You know, make sure you pay good attention to that.
What you are saying here, okay, that we use the right-handed, left-handed positron as a right-handed electron, or?
I said not as a. Either I work with ER or with ER star. It's up to me. One is the complex conjugate of another.
So you mean that they are mathematically the same? Or?
It's the same state. They are not mathematically the state. One is complex conjugate and the other. But if you have a complex number, why do you have to work with Z? You can work with Z star. Just remember that Z star is a complex conjugate of Z, but Z is a complex conjugate of Z star. So which one is more fundamental? This one or this one? One is just a complex conjugate of the other. It's just a notation. I'm confused what is confusing here, but maybe I forgot how confusing it was when
we said that
when I was learning.
We said that left-handed particle, antiparticle. No, let me see.
Well, this is the same. I'm ER. This is ER star. Let me be more precise. Okay. This is I gamma 2 ER star. Someone says I'll work with Z field, complex number. The other guy says no, Z star is more fundamental. Z is a complex conjugate of Z star. There are two states which are independent. One is EL, the other is ER. Period. I can say it another way. There are two states which are independent. One is EL, the other is ECL. Then, of course, there is just one chirality. If I speak of the electron and the positron, then there is EL and ECL. Because ECL is made out of ER. So you have to get to learn to that. And it's here. It's all happening here. A particle entering is equivalent to antiparticle leaving. A particle leaving, look at the electron leaving here. It's completely equivalent to positron enter. The only thing is they are opposite chiralities of each other. Charge conjugation takes left to right, just like Harry. Both are maximally broken in the standard model by definition.
Now we discussed the very first discussion of the weak interactions. We said that we didn't observe any right-handed neutrinos.
No.
So this interpretation has no physical concept.
No, this is a left-handed neutrino. I'm not introducing a right-handed neutrino.
Yes,
I mean,
doing that?
No, this is nu CR. This is not nu R.
So nu CR is...
It's nu L.
But it's nu CR.
No, wait, nu CR is nu L. Did you follow this derivation? Let me just see if I can erase this. Here this was very formal, okay? Once again the physicists. This you have to. It has to enter, it has to be in your guts. For prediction error of guts, as we call grand unification, you have to have this in your guts, in your fingers in your guts. And I'm not kidding, this has to be there. What is nu CR, please? Nu CR, once again, is C nu L bar transpose. Is C nu L dagger gamma 0 transpose. Is C gamma 0 nu L star. It is nu L. I didn't introduce nu R. I just said I don't want to work with nu L, I work with nu L star. Why can't I do that?
So if I put the antineutrino in positron in a doublet, as a weak doublet, it's a right-handed doublet. Does that mean?
Sure. Okay, but it's the same thing. I can write nu L. This is equivalent to write it EC. There will be a minus sign when we go, because there will be I sigma 2. I can show you. Right, of course. There will be a minus sign, and it is manifest there in the interaction. Why? Because neutrino entering is the same thing as EC going out. This is here, these two, 1 and 2, are the essence of particle physics, field theory. And this is very important, because if I work with grand unification, look, in the weak interaction I cannot put here left and here right. That will break Lorentz symmetry. Internal symmetry has to commute with Lorentz symmetry, because otherwise I perform a rotation and that's impossible. Left has to stay left. So if I want to unify them together, I want to unify these particles, I cannot put ER with these guys. I have to work explicitly with ECL, because all my fields must have the same chirality. You will learn that the same thing happens in supersymmetry. Supersymmetry sort of requires you to put the particles together with the same chirality. This is what the course will teach you. This will be, whoever takes it will be the lesson of that course. So whoever likes supersymmetry and whoever likes grand unification must have this in his blood. There can be no confusion about this. You should stop thinking about that.
Well,
yes?
Why we flipped the lepton and neutrino in the second one?
Remember that Q is T3 plus Y over 2. So the upper component has more charge always. Well, because EC is EL bar transpose, that if this guy has T3 minus a half, EC right, once again, is C EL bar transpose. So if this guy has T3 minus a half, this guy has T3 is half. Like the same way that this gets charge minus 1, this gets charge plus 1, and so on. Complex conjugate, this is the sign of the phase transformation. Complex conjugate field has always the quantum numbers which are opposite. Now, what is better that I erase? You want to keep that 1 and 2 and I erase this? What do you feel more needed that I go on? Any vote on this? You need to bring it backward. Okay, I'll erase this. I'll try just to erase this. He was 32 years old when he disappeared in 1938, Marana. So in 1930, was 26. And apparently this is how it would go with Majorana. They're having lunch and they're having new results that arrived for Irene and Joliot-Curie, Fermi and the group. Fermi was not completely stupid. Okay, as you know, one of the greatest physicists of his era. So they had data we didn't make sense. Majorana comes for lunch. He looks at them and he says, well, it's obvious, there should be a new particle called, it should be neutral. And if it has the same mass as the proton, everything fits. Just stays there for 2 minutes. He says, these morons, they don't understand that, okay. And Fermi says he got goosebumps. By that time he knew that the guy was what he was, okay, but he doesn't believe it. But 2 hours later he says it looks good, you know, he's getting goosebumps. So he asked Majorana, please, you must publish this. He will. Two years later, Chadwick found the neutron, you know that, got a Nobel Prize, and comment to Majorana, he says, you see, you don't have to publish. These morons, just give them a little time. They will figure it out anyway. So what is really going on? Let's follow this line. I said that E is going out, so it would look like this. Let's follow our process. 0 nu 2 beta. I have E going out, gamma mu, left, right? The interaction at the first vertex is left-handed. Agree? Then I have a propagator for neutrino. Okay, carry some momentum. It's a virtual particle, carry some momentum, please, you're following. Then I have the second vertex, which is positron going inside. I'm going to use this particular thing. I want to follow. I'm using the 4-component Feynman rule, therefore I have to follow it. So there will be gamma nu. This is, of course, not the same index. This is a different W boson being exchanged. Gamma nu, right. And then EC. It would look like this. Right? This interaction is manifestly right-handed. I can write it as manifestly left-handed, or I can write it as manifestly right-handed. It's up to me. I want to use this notation so that I can use the usual Feynman rules for the Majorana neutrino.
This vanishes if the mass is 0, right?
Sorry?
This vanishes if the mass is 0.
Does it?
I don't know.
I could be wrong, right? After all, not everything I write on the blackboard is correct. I cannot guarantee for everything that I write, but for this particular thing I have to, I'm sorry. What happens when L goes through M? Nothing. It goes through gamma nu, it becomes R. So it doesn't actually. Oh, sorry, you said that this?
If the mass is 0, this...
It better vanish.
Yeah.
Imagine that it didn't vanish.
Will have this
I will have neutrino double beta decay and I would have a Majorana neutrino. Oh, I'm sorry, you said that it's opposite. No, correct. Of course. This is proportional to M Majorana. Because L, when it goes through K slash, gives me right, then it becomes left, and this will give me 0. So this is proportional to this over K squared. You agree? It turns out that the nuclei of this type that people are studying, K, the virtually has to do with nuclear physics. It's big compared to the orders of 100 MeV or something. Okay. It's the measure of the virtuality of neutrino. So here I can ignore neutrino mass. Remember, I always ignore small numbers unless I'm going directly through the small numbers. Okay, obviously. So this is what I promised to you. Neutrino's double beta decay must be proportional as we expect physically. You saw it, Emil, you saw it. It has to be, of course, diagrammatically and then computationally proportional to neutrino mass. Okay. Why? If neutrino mass is 0, I don't have the violation of lepton number, so how can I observe a violation of lepton number? And we write typically, oh, this can be erased. This doublet thing is manifested here, okay? Here is the doublet hidden. Here is the doublet hidden. Neutrino becomes an electron. I see it here, or I see it in the interaction. This, of course, is coupled to doublet. And this. So it turns out that the amplitude for 0 nu 2 beta is proportional, let's write like this, G Fermi squared. There is a murky nuclear physics. I don't give a damn. You don't give a damn. You're even less than me. I think they use P more often than K. I don't know. Or I use P more often than K. I'm sorry. No, forget. This was silly. To emphasize that the things that from particle point physics of view is the strength of interaction, every time there is a W boson at low energies, that's G Fermi. And this must go to neutrino mass, as Emilio pointed out, and there must be knowledge of the virtuality of neutrino. Okay. Have it written, keep it in mind. I'll tell you, you will see why I need it in the future. Now, I don't want to bug you with nuclear physics. All I wanted us to know that the limit tau 0 nu 2 beta, I wrote this before, I write it once again, 10 to the 25 years, is equivalent neutrino Majorana mass, surely less than 1 electron volt. And typically people will quote the half of that. But I want to be conservative. By the way, this is one of the main processes devoted to directly measuring neutrino mass. Neutrino oscillations didn't measure neutrino mass. We interpret them as the neutrino mass. Say a few words, not today, but direct measurements of neutrino mass. What do you know of any? This is one, but the trouble is here that if neutrino is not Majorana, then of course this is not measuring it. So this is useful only if it's Majorana. How would you measure directly neutrino mass otherwise?
We don't know the exact masses, but we know the difference between.
Precisely. In oscillations, we only know about differences. We would like to know the scale of neutrino mass. This is very important. And you will see why. Already, well, we'll start today. Now, yes, please.
In the propagator of the neutrino, we just set a momentum. Let's say B, right?
Here.
Yes. But I don't know, I'm confused because we said that we have two neutrinos which is coming out. So which momentum we taking? Like which direction? I mean, what is the direction of the momentum in this virtual
momentum?
Propagator? Momentum. What is the direction of the momentum in this?
Direction of the momentum of the virtual particle is irrelevant in this case. Because first, the only thing that I have is p squared, so it's not so important. But if you wish at each vertex, I have followed the line like this. Remember, this was my line. E going out, EC entering. So manifestly here, the momentum P would be flowing in this direction wherever I take it. But it doesn't depend on the momentum, and it shouldn't. Okay, it goes for the mass, it doesn't go through K slash. It goes through the mass, the only thing is P squared. You could say that there is a direction of the physical quantum number. The lepton number is flowing, but it's broken anyway, so that's not a big deal, okay? It's broken by 2 units and not by minus 2 units, or whatever. I'm looking at a process if 2 electrons are coming out. I could imagine an opposite process if 2 positrons are coming out. I can't get them here, you agree. I cannot get them here because neutron is carrying the proton, okay? So proton cannot decay into a neutron and the positron. But in principle,
what confuses me is this, that we said that we know that if the propagator, let's say the direction of the time for the propagator
the time
in the opposite direction to the momentum, we set it to antiparticle, and if it's
no, here is we are interested in the final states. Here, of course, it's well defined. No, I'm saying here that electron going out is equivalent to positron coming in.
no, but I'm speaking about the neutrinos. Like
This is a virtual particle. I'm not saying that there it's irrelevant. When I have a physical particle, I'm saying electron going out. It's the same thing as saying the positron is coming in. Physically, quantum numbers why? If you say that the particle going out gets a momentum p and not minus p, that's p is going out as the momentum goes out. But in terms of the quantum number of the particle, of the charge of the particle, when I say that charge minus 1 is going out, that's equivalent to charge plus 1 going in. You'll see it here. Charge minus 1 going out is equivalent to charge plus 1 going in. When I have a field, that's particle coming in. When I have a bar, that's particle going out.
I think what Maxim also the propagator line consists of half particle or
Yeah, sure.
antiparticle. So when we write the propagator, but it doesn't change how the propagator looks because the P is transferred in the same direction, but like the line is composed of 2 particles.
Yeah, sure, really, there is. But remember what it was. It came from here, and it doesn't tell me. That was, this guy had a piece which was nu L transpose C nu L plus nu L dagger, C dagger, nu L star, permission conjugate. This is the piece that contributes, obviously. We found that explicitly. It was neutrino, there were 2 lines going out from each other. This I call 2 neutrinos going inside, entering, right? Whereas in this case, I call this 2 leaving by definition. When I see a complex conjugate, that's a field leaving. When I see a field that's entering, that's a convention that we have in Feynman rules. And this was the situation I had. There were 2 neutrinos going in the opposite direction. Where I defined the neutrino in a certain manner, it's all a matter of words. I defined the neutrino here because I said I'm going to work with this guy which I call neutrino. I could have worked with the complex conjugate of this guy, and that would have, by me, been anti-neutrino. It's a name I gave to it. But it's a name. What is important that no matter what I gave here, I will violate that name. But I could have called this anti-neutrino.
Can't I just drop the arrows because both are essentially the same and just draw lines there? I mean, Fermi.
Well, it's useful for you picturesquely. We don't do like that. The way I did the calculation, I worked with the Majorana spinner, with the 4-component spinner. There was no this. I don't know how to work with that. I had one and the same arrow. I worked like this, as if I didn't want to break the arrow. But that I had to pay the price. Instead of working with the electron, which manifestly is what is happening in the process, I wrote equivalently positron entering. In that case, I can forget about these lines. So really what I did, once again, electron going out, EC entering, and here neutrino propagating. And this is the Majorana neutrino propagating. So it doesn't matter what I say. As long as I remember that here a lepton number will be broken, for sure. E is going out, EC is coming in. I can read it here. And I can write to do my calculation as if I completely forget about the lines of the propagating neutrinos and so on. This is a Majorana picture that we use. Majorana 4-component spinner. Okay. Lepton number is broken by 2 units. In this process, we say by plus 2 units, I have 2 leptons appearing in the final state. I can think of other processes, okay, and I will as I go along, okay? This is the low energy process that people can come up with. What is the other way of measuring neutrino mass? How would you measure neutrino mass, by the way? The end point of the spectrum. Alexei didn't talk about it. You mentioned the electron energy coming out and so on. Never mind. But I want to go on with my issue of neutrino mass in the standard model. And I need to remind you, because it was not clear when I started last time, when I said I can think of effective interaction. Just think going back when people noticed that there were weak interactions. I knew interactions, right? Neutron decaying into proton plus electron, and then someone suggested a neutrino, we call it anti-neutrino, okay, Pauli it was. So Fermi writes a theory. Now, there are 2 ways of doing it. One is you had already your electromagnetic interaction where there was a messenger called photon. So now, you can introduce a new messenger, you have a new interaction. But Fermi says, no, I don't see that. Let me not talk about it. I know, of course, that there could be a photon-like particle. But I won't do that. I will just write interaction. I have 2 ways, in other words. Now, introduce a new messenger, or use only existing. What will the new messenger here? Well, something that couples electron and neutrino. We call it double. When I am at energies which are far from MW, it's more convenient to do what Fermi did. Fermi did, I won't do that. I will just look at the effective interaction, which is called Fermi interaction. And I write only spinors. Let me write symbolically. So someone now tells you the neutrino has a mass. Now you know. That's going to be new physics beyond the standard model, because in the standard model you and I saw neutrino was massless. So I have 2 ways of doing it. You can do it a la. You can look for that new messenger. That's what I did. I'm still looking for a new messenger. I spent my good portion of my adult life, looking for that new messenger. Or you can do the way Fermi did. The same fellow Weinberg, they didn't want to introduce neutrino, said, well, now you tell me that neutrino has a mass. Says, what would I do? I'm going to use only existing states. So now I have a situation that neutrino mass is non-zero. I'm still sticking to this. This is my standard model. So remember our logic. We said I can write UL transpose C nu L. It must be of this form. The mass term for neutrino must be Majorana because there is only nu L. I'm following Fermi. Fermi didn't know this language. We call it the language of effective field theory or effective interactions. That means describing new physics with the same states and thought of imagining that there will be a new messenger, but it's heavy. So we ignore its momentum. We integrate it out, we often say. We forget about it. At the end, it turned out that it was good to look for the... By the way, in the Fermi theory, Weinberg did the opposite. I tell you, this is interesting. Weinberg actually looked for the messenger, and he made a fortune looking for a messenger, literally. Not only symbolically, okay. I'll tell you why I say this. So we said, and you help me here, this of course cannot be okay because it violates SU2 and U1. So therefore I have to keep adding something to save SU2 and U1. And V was 2 of neutral. This is 5-0. Right? This is not okay. Of course, it doesn't have a nice SU2 form. And this, like the Fermi interaction, it's manifest here. You see, when you have a mass dimension here, that means you have kind of integrated out. That was actually a propagator. But you forgot the momentum. So we said, let's call this lambda nu. You see why this is very important? By this reasoning that Weinberg uses it, neutrino must be Majorana. In the effective language, which says that the new particle states are heavy, which was what Fermi assumed here, he said, if there is new physics, it's going to be done through a heavy particle. Not some very tiny coupling and light particle, but a very heavy particle, therefore I just won't propagate it. By the analogy, this is a dimension 5 operator, this was a dimension 6, this is just G Fermi's M squared, and this is why I wrote lambda nu here, dimension 5. The message is that the picture that Majorana imagined is a must here. We will predict if the new particle states are very heavy, the neutrino is a Majorana. It must be. It has an assumption, of course. Now, how would you write it in the operator form? I'm about to finish. Oh yeah, I started at 20 after we started. Let's just spend 2 minutes, and I want you to think for Wednesday a little bit. If you have a few minutes, talk to each other. If you can think of some other operator. How would I write it in the SU2 language? I cannot work with neutrino. There is no neutrino. There is this. You can bear with me a few more minutes? Please.
It's a doublet in a doublet.
Okay, so I start with a doublet maybe. This would be a natural thing. But notice, not good, sorry. This is Lorentz invariant, but I have to make it SU2 invariant. So how would I make it SU2 invariant?
You can put the fields inside. Yeah.
Sorry? I have 2 doublets. How do I make? What could I do? Cannot put 2 doublets. 2 spins. What I could do? I could.
have C in right?
C is Lorentz. It's not SU2. No, I'm talking about SU2 weak. Sorry, SU2 left. SU2 gauge. SU2 Gleshov. Weinberg. Salam. Not SU2 in the Lorentz. Okay. So this is invariant under Lorentz, but it's not invariant under SU2, obviously. When I have 2 doublets, phi 1 transpose, phi 2 is not invariant. This goes into phi 1 transpose, U transpose, U, phi 2. This is not 1. No, what do we do here? Huh?
Gamma 0 something like gamma 0.
Lorentz, gamma 0 is Lorentz.
Yes,
SU2.
No, in this context, we need something like that works like gamma 0 for spinors.
No, you need something. There should be something which is more fundamental. Okay, spin. What did you do in quantum mechanics? You anti-symmetrize. I sigma 2. This is Lorentz. By the way, when I want to concentrate on SU2, I don't write Lorentz C. When I want to concentrate on Lorentz, I don't write this. But really, it should look like this. This, of course, is invariant. Because now this is anti-symmetric, that's invariant. If I put I sigma 2, then it's okay, because this is phi 1 transpose. I sigma 2, this guy when he commutes becomes U dagger. U phi 2. And this is 1. Now notice, it can't be like that. Because this would be a singlet, so it would look like neutrino electron. I sigma 2 picks up an electron. But this would be the most natural thing in the world, and you can see they cannot be like that, because then you have to write the Higgs. Then you would write phi transpose, I sigma 2 phi, which is a possible invariant. Remember I told you about the 0, because this is symmetric, these are bosons. And this is anti-symmetric. So this obviously is 0. So this cannot reproduce this. After all, this is a triplet. It has T3 minus 1, minus a half, minus 1. Okay, I'll finish on this. Just to remind you, and I invite you, try to do it without looking anywhere. If you cannot, on Wednesday I can send you, I have a certain review on the basics of neutrinos, which I never cleaned enough to send it to the archive. But I can give it to you, for those of you I'll send you. Notice, this of course is invariant, but this also. Okay, I put C because I put I sigma 2 because otherwise this transpose is killing me. But I can make a triplet by sandwiching Pauli matrices. When you sandwich Pauli matrices between two doublets, you get a singlet. You get a triplet. This was the adjoint way of writing, really, which is hidden in remember when you write your covariant derivative for SU2, there is I mu minus IG, PA, A mu A. And these are Pauli matrices, really. You sandwich this between two doublets. So, side comment. So this will be invariant. Phi transpose, I sigma 2, sigma phi. We'll continue on Wednesday. I have a challenge for you. Try to think of equivalent, maybe even simpler, more elegant ways of writing. This is surely correct. This will reproduce this. It takes some algebra. To reproduce it, please write phi is 0, phi 0. My unitary. Show, if you can, if you have a few minutes, it will help you to follow the lectures that are coming. Show that you get this. And then you don't get E electron, something that will violate charge, okay, that you will be worried, okay. But I really more challenging thing for you guys. Think if you can find another way of writing this, more elegant. Something along this, which didn't work. This didn't work because this is 0. But I could try doublet, just a little thinking over rearrangement. Okay. Enough. Took a few extra minutes. Any last public question?